All right, folks, please find your seats. We need to get started with our show. Alrighty, everybody, we just got our okay to start our planetarium show. So I've put away our space trivia questions because now, folks, we're going to be heading into the unknown. And welcome, everybody, to the Morrison Planetarium. My name is Christian. I want to be your planetarium presenter. And just a heads up, I'm not just a voice coming out of the walls. I'm a person, and I'm standing right behind you at the very top of the planetarium. Hey, good afternoon, everybody. Don't hurt your next foot, though. Look forward into the dome before you. Everything that you see in purple is going to be one really big screen, thanks to the help of 6 different projectors hidden throughout our planetarium dome. And folks, the show that we're going to be doing right now is one of my favorites. This one's different from all the other planetarium shows that we've done here today. This one's called Tour of the Universe. And so for the next 30 minutes, you're going to be hearing my voice because this show is completely live as I free fly us through space. And we're going to be starting off pretty close to the Earth, and we're going to be zooming all the way out to the very edge of the observable universe. Hopefully by the end of the show, you won't have an existential crisis of where we are in space, but just a heads up, we're pretty small in the grand scheme of things, so just a forewarning. And before we get started with our tour of the universe, I do have to go over some quick house rules, just so that we're all on the same page and have a good time in here. First off, folks, there's no food or drinks allowed in. If you manage to bring any snacks or beverages, make sure those are put away till the end of the show. We want to keep this place as clean as possible. We greatly appreciate your help. Also, if you happen to have any cell phone smartwatches, now is a good time to put those devices away for the next 30 minutes, as these can be very distracting and takes away from the planetarium show experience. And folks, if you need to exit early, the exits are going to be at the very top of the planetarium, so always make your way up the stairs to exit. If the stairs are too steep for you, do not worry, just remain seated. Once the show's over, we'll have a staff member escort you to a lower exit so that you don't have to climb those steep stairs, so just stay seated for a bit longer. And also, folks, this show is very immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you start to experience motion sensitivity, there's a really quick and easy trick to ground yourself. All you have to do is close your eyes, take in a few big deep breaths, then your brain will remember that you're sitting in a planetarium in San Francisco and not hurtling towards the edge of the observable universe. At least not more than the usual. Hee hee hee. But with that being said, it looks like we're ready to go. So I invite y'all to sit back, relax, and let's begin our tour of the universe. All right, everybody. As I mentioned, we're going to be starting off pretty close to the Earth. We can see the curvature of our planet and the city lights down below, but we're going to be starting off at this really cool spacecraft in front of us called the International Space Station, or the ISS for short. And a lot of people tend to ask me, hey, Christian, what is the International Space Station? I always heard about it in the news and the articles, but I don't really know what it is. Could you explain it for us? Well, of course, folks. The International Space Station is a research facility. It's a laboratory that orbits around our planet, and they conduct many different types of science experiments up here. Some of the things that they'll conduct are things like what happens when you try to grow plants in space, which way do the roots grow, and another one is what happens when you try to spark a match in space? Does the flame act the same? Does that act differently? So lots of different types of science experiments are conducted here on the ISS. And this thing looks really big here in our planetarium dome, but it's not that big in actuality. The ISS is only about the size of an American football field. If you've never been to an American football game, that's okay. You can also use the entire California Academy of Sciences, the museum we're sitting in right now. That's about how big it is. And also, what's really impressive is that this thing is going incredibly fast. The International Space Station is traveling at a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And also, this looks really far away from our planet Earth as well, but the ISS isn't too far away. It's only about 225 miles above the surface of our world. 225 miles, that's not too far away. That's like going from San Francisco to Santa Barbara, a nice little road trip to get away with the family for the weekend, so not too bad. But to tell you the truth, folks, this is as far as we put humans into space nowadays, only 225 miles above the surface of the world. The reason why is because traveling into space is very expensive. You got to build yourself a rocket ship, buy yourself one, or pay for a ride. And then once you acquire that, you have to account for all the rocket fuel. You got to be able to escape the Earth's gravity. And once you acquire all that rocket fuel, you have to account for all the food, water, all the air you're going to be breathing while you're up here in space. So the bill gets quite costly quite rapidly. But the International Space Station is just the first stop on our tour of the universe, so now we're going to see it slowly fade away to the city lights down below. And before we lose track of it, I want to add a nice little orbital path so we can see it as it slowly disappears. And now, folks, we're able to see our entire planet Earth from this perspective. And I want to let you know that the space program that we're using here inside the Morrison Planetarium is something that you can go home and download if you want to fly through space just like how I'm doing. The program that we're using here is called OpenSpace. So if you go to your favorite search engine, type in OpenSpaceProject.com, you'll come across the link where you can download this, and it's a whole lot of fun. And just a forewarning, OpenSpace isn't finished. It's in its beta phase, so we may come across a few bugs and glitches. If we do, I'll point them out. Hopefully we can look past them. Also, OpenSpace uses a whole lot of processing power. So if you have an older computer, it may overwhelm it. But if you got something new or a gaming computer, give it a try. It's a whole lot of fun. But in here, we're using OpenSpace. But now that we got a sense of what we're using, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. This was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science. Of course, they had some fun up here as well. They got to play some golf. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission in the works called Artemis. Pretty much with Artemis, NASA wants to send humans to Mars. But before we send humans deep into the solar system, we got to figure out exactly how we're going to be living out here in space. So the moon is the perfect stepping stone how we're going to be figuring out the logistics of doing that. And what's really amazing is that they're going to be sending the first woman to the moon. But not only that, they're also going to be sending the first person of color to the moon. But not only that, they're also going to be setting up lunar bases throughout our moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to conduct much more science in a much more compactable size. And one place that we definitely want to set up a lunar base is the South Pole of the moon. The reason why is because we found ice there. And ice is going to be helpful because we can melt that ice, pass electricity through it, we can separate the hydrogen and the oxygen, and both that stuff's valuable when you're far away from home. So we humans should be heading back to the moon relatively soon. Just look out for any news about Artemis. And folks, when we look up at the moon here from planet Earth, the moon feels incredibly close. Feels like you can reach out your arms and touch it. But the moon's incredibly far away. It's about 240,000 miles away from our planet. 240,000 miles. Some of the adults in this room may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove about 4 months nonstop, going about 80 miles per hour. Although I wouldn't recommend it. The roads out here are poorly maintained. Hee hee hee. And from here on out, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so or since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind, so everybody say bye-bye, moon. So cute. And now, folks, we're going to see the moon as it starts to slowly fade away, just like how we saw with the International Space Station. And just like before, I want to add some planet trails so we can keep track of the moon and all the orbits in our solar system as it starts to slowly fade away. Because again, space is really, really big. And on our journey today, folks, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to computer models like OpenSpace showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view. So here comes the sun. Do-do-do-do-do. And the sun is also incredibly far away from our planet Earth. It's about 93 million miles. Whew, that is a good distance away. 93 million miles. In order for sunlight to travel that distance, it only takes sunlight about 8.5 minutes at the speed of light. So really fast. And this is a great concept to keep in mind, folks, because as light is traveling through space, it takes a long time to reach a certain destination. For example, let's say we're looking at a star that's 70 light years away from us. We're looking at that star as it looked like 70 years ago because the light that just reached us took 70 years to get to us. So when we look at really far away objects in space, it's like looking back in time in a sense, which is really cool. But now that we have a nice bird's eye view of our solar system, let's do a quick refresher of what we have here. Right in the middle of our solar system, we have the biggest thing, our star, the sun. Closest planet to the sun, we have Mercury. Then we have Venus. It's really hot there. And then Earth. That's us. And of course, we have the famous red planet, Mars, coming into view. And these are all the rocky terrestrial planets. These are places where we can actually land a spacecraft on. And then past the orbit of Mars, we have our main asteroid belt. And this is what it would look like if we highlight all the asteroids in the asteroid belt. There's roughly about 1 million of them here. And then past the asteroid belt, we have the really big planets, the gas giants, the Jovians. We have Jupiter, the largest of them all. Saturn, famous for its rings. And then we have our icy gas giants. We got Uranus, the funny one, and Neptune. And of course, we can add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And you're probably wondering, what's the Kuiper Belt? I've never heard of that before. Well, folks, this is the Kuiper Belt. Yeah, that's a lot of stuff. And the Kuiper Belt is like a second asteroid belt way out here past the orbit of Neptune. What you're mostly going to find out here are icy asteroids and short-period comets. Comets that don't stray too far away from the sun. And what's really fascinating is that in 2006, our technology, our telescopes greatly improved, so we're able to see much smaller objects much further away. And in 2006, we found more than 400 objects out here in the Kuiper Belt region. Some of this stuff was bigger than Pluto. And we couldn't call all these things planets. There was just way too many of them. So all the astronomers on planet Earth had a great big meeting. They had to figure out what exactly you need to be considered a planet. And they came up with 3 criteria. And folks, that was the day in 2006 that Pluto went from being a planet to a dwarf planet. But that's the really cool thing about science, because as our technology improves, we're able to make better observations. And so that's the really fascinating thing about science. It's constantly updating and changing. But I'm going to put away the Kuiper Belt because that's just a whole lot to look at. And now I'm going to be adding on screen some many different spacecrafts we sent out in the 1970s to explore our solar system. So now on screen we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. Now all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventurers, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to go all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours, not too bad. But now, folks, it's time for us to leave our planetary scale behind us, because now we're heading out into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And it looks like Alpha Centauri just flew over our heads. Again, we're right in the center of our screen. Alpha Centauri is the star that's moving closest to us on the left-hand side. And again, 4 years at the speed of light just to reach the next star system to us, folks. But that doesn't put into perspective of how long it would take us to travel that distance. Folks, if you're to get in a rocket ship today, make your way over to Alpha Centauri, it's going to take you roughly about 8,500 years. And that's just a one-way trip. But let's stop and consider whether humanity has made its presence known beyond our solar system, because now, folks, we're going to be stepping inside something called the radiosphere. And again, we're now inside something called the radiosphere, and this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And it extends about 90 light years in all directions, emitting out from the Earth. This first began in the early 1930s with strong radio waves, early television, radar signal, and then later, the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before the early 1930s, but the earliest radio was not quite powerful enough to escape the Earth. Since all these signals are electromagnetic, they are traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year, so is anybody out there listening? And now, folks, I'm going to be adding these many markers onto the screen. These markers indicate many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 5,000 confirmed exoplanets in the nearby vicinity to us. 5,000 other worlds besides our own. And that 5,000 number is going to be increasing as the years continue because we have space telescopes where their whole purpose is to find as many exoplanets as possible. In fact, if you look towards the top of our screen, you'll see a whole bunch of exoplanets. We pointed our telescopes in that direction for about 10 years and we found a whole heap of them. So as they scan more and more, that 5,000 number will be increasing. Now, to say if any of them are Earth-like with conditions suitable for life as we know it, well, we cannot answer that question quite yet. Pretty much new space telescopes are being developed, created right now, so we got a few years before we can answer that question. But the more important point here is that quite a few of these planetary systems are within that 90 light-year limit of our radiosphere and could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. And of course, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will. Because the radiosphere is always growing, but it becomes weaker as it does. And I want to put away these exoplanet markers for now, but I'm going to leave our radiosphere up on screen. As huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. So let's continue zooming on out. And now, folks, we're looking down on our Milky Way galaxy. This is the galaxy we live in, and I have to ask, can anybody see their house from here? And folks, our Milky Way galaxy is really big. If you wanted to cross it from one side to the other, it's going to take you roughly about 130,000 years at the speed of light. It is enormous. And our Milky Way galaxy is so huge, we estimate that there's at least 300 billion stars in our galaxy. If our recent discovery of so many exoplanets just within our small neighborhood, within this vast star city is indication, there could be potentially billions of planets and potentially millions of Earth-like planets throughout our single galaxy. And I also want to show you the shape of our Milky Way. As we spin around to the side, you're going to notice that our Milky Way galaxy is really flat. It kind of looks like a big pancake or frisbee in space. And this is important because when scientists and astronomers want to learn about the universe, it's so much more easier for them to point their telescopes galactically north and galactically south, instead of looking to the plane of the Milky Way, which has planets, stars, gas, debris, things that block their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south. That's going to come important in just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. And we live in a local galaxy group which contains about 30 galaxies large and small. Also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door, and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as we continue expanding out, folks, you're not going to realize that galaxies are not evenly distributed throughout space. Instead, galaxies like to clump together in large groups and clusters, or they create voids where there's very few galaxies or no galaxies at all. So you can kind of think of galaxies like people. They like to hang out together or they like to avoid each other. And this picture that we're looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing researcher by the name of Dr. Brent Tolley, who works at the University of Hawaii. And he compiled this map over decades of time with other astronomers working aside him. So big shout out to Dr. Brent Tolley. I love flying through this map. But now, folks, we have automated systems that are mapping even the most distant galaxies. So now we're about to see the very large-scale structure of the universe. And remember, folks, every single point of light that you're seeing, that's not a star, that's an individual galaxy. And by the way, the large-scale structure of the universe is not in the shape of a bow tie or a butterfly as we start to swing around. Remember when I mentioned that we live in a big flat spiral disk of the Milky Way? Well, if we were to line up our Milky Way galaxy, it would line up just right down the middle, just like so. And again, we like to point our telescopes galactically north and galactically south, instead of looking to the plane of the Milky Way. But astronomers still want to make sure that there was galaxies through our Milky Way. So you see this purple survey of galaxies, they were still able to find them, just not as many and not as far. Pretty much we have to wait for our technology to improve, and once that happens, we'll be able to fill in all these areas that haven't been filled in yet. So it's just a matter of time. Whew. And speaking of time, we're almost out of time. So let's continue pressing on, folks, because now we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars are going to be represented by orange dots on either side of the large-scale structure of the universe. And unfortunately, we don't have a visual of quasars. I highly recommend you look it up. They are very powerful objects in space. And look at how many quasars are all the way out here. And quasars are short for quasi-stellar radio sources. These blazing objects are all billions of light years away, so now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the very edge of the observable universe. What we're looking at is something called the Cosmic Microwave Background Image, or the CMB image for short. And all evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this isn't your typical photo either. Instead, this is a temperature density image, where the light echoes of the Big Bang are color-coded, with the lighter areas corresponding to the hottest, least dense regions, and the darker areas the coolest, densest regions. These fluctuations in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But these tiny differences eventually gave rise to that large-scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is of the outer edge of the known universe, folks, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we've traveled as far back as the law of physics can physically allow us to go. So we only have one direction left to go. That's going to be back home towards planet Earth. So let's find a nice entry point to all these quasars and galaxies. And this looks like a good spot. So let us make a return trip back to planet Earth, everybody. All right, everybody, we're crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, everybody, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we're making our way back into our Milky Way galaxy. We're heading straight for that radiosphere. And now we're making our way back to our star system, our solar system, our little neighborhood in the vastness of space. And now we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto and the Kuiper Belt region, and making our way to the third rock from the sun, our homeworld, planet Earth. All the people that we know, loved, ever learned about in history all lived on this one planet. And now we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And as we make our final approach back to planet Earth, folks, this is going to be the end of our Tour of the Universe show. And if you want to share this exact show with someone who was unable to make it today, this show is recorded on the Morrison Planetarium's Facebook page or the California Academy of Sciences YouTube page. So feel free to share this show with anybody who missed out. But hey, look at that. We made it back home safe and sound just in time for dinner time. And that's all the time that we have for today, folks. I hope you get home safe, and thanks for stopping by.